This episode is sponsored by Winston Hugh. Today, we're going to tackle a problem every AI developer faces: how to transform those fragile proof-of-concept scripts into truly scalable, robust systems. We'll be using a framework I call Architecting AI, the 4+1 patterns, to move from that initial chaotic code to clean, enterprise-grade software.
So here's our game plan. First, we'll pinpoint exactly why those initial scripts are so problematic. Then we're going to build our way out, step by step, with 4 foundational patterns: the registry, the pipeline, the adapter, and hooks. Finally, we'll tie it all together with the +1 pattern, the agent core, which is what really gives the system its intelligence.
You know the script I'm talking about. It's the one that gets your demo working. But it's also a complete mess, a tangle of business logic, data processing, and raw API calls all in one place. Trying to scale that? Forget it. It's impossible to maintain, a nightmare to test, and it breaks if you so much as look at it the wrong way. Our job today is to enforce some structure, some real discipline, using these proven architectural patterns.
All right, first up, pattern 1, the registry. This one is all about how you select tools or strategies. You know, when your agent has to decide between using a calculator or a web search or some drawing tool. The beginner's approach is just a giant, ugly conditional block. That if-elif-else chain quickly becomes a major bottleneck. The registry pattern is a much more elegant way to handle this. And let's be explicit about the problem here. It's not just about 3 tools. What happens when you have 10 or 50? That central if-elif-else block just explodes in complexity. Every time you want to add a new tool, you have to go in and modify that core logic. It's slow, it's error-prone, and it violates some really fundamental design principles. What we need is a way to completely decouple the tool's implementation from the logic that selects it. The solution is surprisingly simple. At its heart, the registry pattern is just a class that holds a static dictionary, that's our registry. Then, you create what's called a decorator factory. We'll call it register, and it takes a name as an argument. Exactly. When Python loads your module, it sees the decorator on top of your function. That decorator's code runs, and it automatically adds the function to that global registry dictionary using the name you provided as the key. It all happens at load time, before a single line of your main logic even runs. And this slide just says it all, doesn't it? On the left, you've got that brittle, ever-growing if-elif mess. Every new tool means editing that block. But on the right, that's the declarative way. A developer just writes their tool function, slaps the @toolregistry.registerDecorator on it, and they're done. The core selection logic shrinks to a single, beautiful line, a dictionary lookup. Tool registry get tool name. It is clean, it's dynamic, and it's totally decoupled. So just to be crystal clear, this means we can keep adding new tools and we never once have to touch that central piece of selection code? That is precisely it. And that brings us to a critical architectural principle, the open/closed principle. Our system is open for extension. You can add 100 new tools if you want, but it's closed for modification. That core dispatch logic is finished. It never needs to change. This isn't just a trick. It's foundational for building robust software. Okay, so we've organized our tools. Now let's talk about data flow. In AI, especially with something like RAG, you have all these processing steps. You load data, you clean it, you tokenize it, you vectorize it. If you just chain all that in a single function, you get what I call variable soup. The state of the data becomes incredibly difficult to track. The pipeline pattern is how we bring order to that chaos. The concept here is really straightforward. We start by defining a single context object. You can think of this as a data packet that's going to flow through our system. Then, each step in our process, cleaning, tokenizing, you name it, gets encapsulated in its very own processor class. The main pipeline controller just loops through a list of these processors, handing the context object from one to the next. Let's walk through a concrete RAG example. We create a context object and put the raw PDF text in it. The first processor, our cleaner, modifies that text attribute in place. Next, the tokenizer reads that clean text and adds a new attribute to the context called tokens. Each step is atomic and totally independent. And here's a key feature. Any processor in the chain can just return false to immediately stop the entire pipeline. This is absolutely essential for things like validation and error handling. Let's be honest, the LLM landscape is a bit of a mess. Calling the OpenAI API is completely different from calling a local model with a llama, which is different again from calling Anthropic. If you hard-code these specific API calls into your business logic, you're creating a future maintenance nightmare. The adapter pattern is how we solve this, by creating one single, unified interface. And I mean, just look at this. The differences are stark. OpenAI needs client.chat.completions.create. Ollama just wants client.chat. The parameter names are different, messages versus prompt. The entire data structure is different. Without a proper architecture, your code is just going to be riddled with if-else blocks, trying to handle all these variations. It's a disaster waiting to happen. So the solution is abstraction. We start by defining an abstract base class, let's call it LLM base, and give it a standard method, like .chat. Then we create concrete adapter classes, like OpenAI adapter and Ollama adapter. Each one of these inherits from LLM base and implements that .chat method, but inside it hides all the ugly provider-specific details. The different API calls, the parameter mapping, the key management, it's all hidden away. So the main application code just calls a standard .chat method, and it has absolutely no idea if it's talking to OpenAI or a local Llama model. That is the power of it. Your main business logic is totally decoupled from the LLM implementation. The code is initialized with an object of type LLM base. It doesn't know, and it doesn't care if that object is an OpenAI adapter or an Ollama adapter. It just knows it can call the .chat method to find in the interface. This is a classic textbook example of polymorphism, and it's what lets you hot swap your model backends without changing a single line of your core logic. Okay, pattern 4. Think about long-running processes, like training a model or scraping a massive dataset. We often need to inject some logic at specific points, maybe for logging to a dashboard, saving a checkpoint, or checking for an early stopping condition. The naive way is to just keep adding more if statements inside your main training loop. That gets messy fast. The hooks pattern gives us a clean, event-driven way to do this. The best way to think about this is as a broadcast system. Your main trainer class has no idea what any monitoring functions might want to do. All it does is maintain a list of these functions, which we call hooks. Then, at critical moments in its process, say at the end of an epoch, it just iterates through that list and calls every function, passing its current internal state, like the epoch number and the current loss, as arguments. It's broadcasting an event, and anyone can listen. All right, we've come a long way. We've built the individual components, a toolbox with the registry, a data assembly line with a pipeline, interchangeable brains with the adapter, and a monitoring system with hooks. Now it's time for the +1. This is the pattern that orchestrates everything into a thinking, looping, self-correcting agent. And we do it by combining two classic patterns, the blackboard and the state machine. First, the blackboard. This is the agent's central nervous system, its shared memory. It's just a single shared object, we'll call it agent state, that every single component can read from and write to. It holds the user's query, the conversation history, a log of the agent's thoughts and actions, and, most critically, a list to track errors and a done flag to stop the loop. This shared state is the absolute key to coordinated, intelligent behavior. And this is the fundamental shift in thinking. Our pipeline pattern was linear. It ran from start to finish and then stopped. But a real agent doesn't stop. It thinks. It operates in a continuous loop, while not state gun. It assesses its current state, it acts, it observes the result of that action, and then it reassesses, starting the cycle all over again. This loop is what separates a simple script from a truly autonomous agent.
Let's break down this cognitive cycle. Step 1, decide. The LLM adapter, our brain, reads the entire agent state object to figure out what to do next. Step 2, execute. The chosen action is dispatched using our tool registry. Now here is the absolute most important part. Step 3, log error. If the tool fails, maybe an API times out or there's a math error, the exception is caught. It does not crash the program. Instead, the error message is written into the agent state's errors list. So on the very next loop, when the brain looks at the state, it sees the error from the last attempt and can formulate a new plan to fix its own mistake. This is the core mechanism for self-correction. So let's put it all together. The registry decouples your tools. The pipeline structures your data flow. The adapter standardizes your LLM calls. Hooks give you non-invasive monitoring. And finally, the blackboard and state machine combine them into an intelligent, resilient agent that is actually capable of learning from its own mistakes in real time. This is how you go from a fragile demo to real, scalable AI software. Special thanks to our sponsor, Winston for making this deep dive possible. Go refactor your code.